Hi guys, these are your notes for section 9.3 and this is on continuous compounding. Generally I don't really like finance type sections, but I find this section really interesting and I hope you do too. Basically what we're going to look at today is we're going to look at what happens whenever interest is compounded all the time, okay? And something kind of surprising happens and I'm going to talk to you about that today. Okay, here's a journal choice for you. In case you're interested. Let's talk about interest. Okay, what do you know about interest? Well, you should recall a formula. A equals P times 1 plus R over N to the NT. Okay, we talked about this, I think in chapter maybe 7. And you should have this memorized because that's come back a couple times on tests. Number of times compounded is the n variable here in the formula, and that's where we plug in how many times you can compound it. We can plug in lots of different things for that. If it's annually, just once a year, we plug in 1. If it's semi-annually, we plug in 2. If it's quarterly, we plug in 4. Monthly, 12. Daily, 365. Is there a limit to how many times we can compound that? Can I go to the minute? Can I go to the second? Can I go to the fraction of a second? That's what we're going to talk about today. And I think you guys would say, yeah, let's do it by the minute, or let's do it daily. Because what we found when we talked about interest, the more times compounded, the more money you make. So if we go down to that second, what's going to happen to our money? Well, we'd expect to make quite a bit more, and that's what we're going to look at today. Okay, suppose you put $1 into a bank account. If the bank were to pay you 100% interest, which no bank really does, but for the sake of argument, that's what we're going to use for this example, your money would double in 1 year because it's going to be annually. Number of times compound is going to be 1. $1 at 100%. In 1 year, we're going to have $2. Okay? If we did semi-annually, we're going to make more than $2. In fact, we're going to make $2.25 because now the number of times compounded has changed to 2, and this is 2 times 1, but they didn't write it down there, and this is the formula I just wrote down. So this is exciting. We are going to fill out this chart using that same formula. A equals P times 1 plus R over N to the NT. We're going to look at different values of N, the number of times compounded. The principal is going to be 1 for all these, okay? The rate is going to be 1 because we're talking about 100%, which is not common, obviously. It doesn't really make sense. But we're going to use that so you can see what's going to happen here to the pattern. We're going to change this N up, and we're always going to do 1 year, okay? So if we do annually, plug in 1. That's the first one we talked about. This is the second one. If we do it quarterly, I'm plugging in 4 here for the number of times compounded. The exponent becomes 4, and now we make $2.44. Things are looking good, okay? If I do monthly, we're going to change N to 12. And we're going to have 1 plus 1/12 to the 12th power. And you type that in your calculator. And I get $2, and now we're looking at 61 cents and some change. Little partial pennies, they might add up if we're talking about big amounts of money. Daily, 365. 1 plus 1 over 365 to the 365th power. How much are we going to make? Looks like $2.71 and some partial pennies. Okay, how about hourly? Well, how many hours are in a year? 365 days times the 24 hours a day, and we get 8,760. Plug this in, and something kind of surprising happens. At least it's surprising to me. It's still going to be 271 and some partial pennies. Not a very big jump here at all, okay? And we changed the number of times compounded quite a bit. So when we look at what happens by the minute, we take that hourly times 60. You get something very large. And you plug that into your calculator and we get $2, and you guessed it, 71 cents and some partial pennies. And the change is even smaller now. Tenths, hundredths, thousandths to the 10,000th of a penny. Okay, so what happens? Well, you started with $1 and this is getting closer and closer, and it's rounding out here at 271. Okay, this 271 is actually it's an irrational number. It's very much like pi. You guys remember pi, 3.14159, yada, yada, yada. This number, this 2.71, actually has a name, and its name is E. It's named after a guy named Euler, not Euler, but we call him Euler. It is an irrational number. It does go on forever and ever and ever. And the way that they can figure out what it is they would just keep making this number larger and larger and larger and taking it to that exponent power. And here are the first 50 digits, okay? You don't obviously need to know them. Usually when someone says, what is E approximately, we say it's approximately 271. Okay, just like they use 3.14 for pi, we use 2.71 for E. It has lots of applications, mostly in finance. But you will use this again in your future, and you'll use it a lot, actually, in calculus. Okay, this is quite a bit of writing on here. What value does your calculator display for E? Let's talk about using your calculator. There should be e to the x key on your calculator, and we usually deal with taking e to some exponent. So if you type e to the first power, that should give you close to 2.71. I have my Inspire out right now. I'm typing e to the first power, and it just says e. If I type e to the first power and then I hit a decimal point afterwards, it says syntax error. So you guys probably are going to be better at this than me. How do I get this to tell me? Okay, if I e to the first power decimal point, mine says 2.71828. This is not exact. It is approximate. It is rounding it off, okay? E goes on forever. But you do need to find that key on your calculator because you're going to be using it. This is true. Savings institutions do not pay 100% interest rate. That was ridiculous to think of. But the number E appears regardless of that interest rate, okay? If I type in this 0.04 for 4% interest rate, you still, the more times compounding, it is cutting off here, if you will, okay? And what this is actually cutting off to is e to an exponent's power, and the power just happens to be 0.04 for that 4% interest rate. If you don't believe me, if you type in your calculator e to the 0.04, you will see that it's 1.04081 approximately. Okay, so this is e to a power is what this is. So basically the formula that we are used to, this a equals p times 1 plus r over n to the nt, will change a little bit when you're compounding continuously. You could type in a massively large number here, but to get more of an exact number, we are going to take out this 1 plus r over n, and we're going to change that to the number e. Okay, so the formula becomes, on continuous compounding, a equals pert, p e to the rt, and this used to be easier for kids to remember because there used to be a shampoo called Pert, like Pert Plus or something. It was like a green bottle, and they used to do lots of commercials. I don't really think I've seen that in a long time, that commercial, but that is the formula right here. It is very much like this. You take out the parenthesis and you're replacing that with e. Okay, so let's compare the two formulas. What type of functions are they? A equals p times 1 plus r over n to the nt, and a equals p e to the rt. Okay, what type of functions are they? Well, they are both exponential growth functions. E is a number bigger than 1, so it's exponential growth because it's about 2.71. And this is going to be bigger than 1 because it's 1 point whatever r over n is, because 1 is being added to it. So they are both exponential growth. What are the growth factors? We just said that. That's going to be 2.71 for the new one, for the continuous compounding. And then the regular interest formula is going to be 1 plus r over n. Why would institutions ever continuously compound? Okay, well, this is the reason why. Let's talk about daily compounding. A is P times 1 plus r over 365 to the 365. Versus A equals PE to the RT. E is just a number. It holds a place in your calculator. This formula is easier. It's quicker to use than this one up above. Let's talk about what the difference actually ends up to be. Let's look at an example. Let's say that we have $850 invested at an annual rate of 6%. And let's compare let's just do annually to continuously. Let's see what happens. Okay, so I'm going to erase this. We won't even do daily. We'll just do annually versus continuously. So A equals 850 times 1 plus 0.06 over 1. So you don't even need to write that. Let's just look at 1 year. And if we do it continually, A equals 850 e to the 0.06 times 1. And let's see what we get here. If I take 850 times 1.06 to the first power, I'm going to get $901. And if I take 850 times e to the 0.06, I'm going to get $902 and 56 cents. Alright, so in 1 year's time, the difference is $1.56. Okay, is that going to make or break a bank? No, it's not. Basically, these two numbers, as long as the time is not massively, like if you're going over 20 or 30 years, then the continuous is going to cost the bank a little bit more money. But if you're looking at a short investment time, the difference isn't that substantial. So the difference isn't really worth it unless you're looking at a very long time of investing, in which case that second exponent will come into play and E will make it quite a bit bigger. Okay? But the difference isn't worth it very much for banks, so a lot of times they will continuously compound. I wouldn't say a lot of times, but sometimes they will. Just because of simplicity of the formulas and working and saving time working on the numbers rather than using the more complicated formula. Okay, let's talk about Mona. She invested this amount of money in a zero coupon bond paying 4.5% compounded semi-annually. After 25 years, the value of the bond will be this. How much would Mona's investment have been worth after 25 years if the interest were compounded continuously instead of twice per year? Okay, so she would have had $25,000. Let's see how much she would have had if it was continuous. A equals PE to the RT. The principal is $8,218.16. E to the rate, 0.045 times T, which is 25. Be careful when you plug this in your calculator. I'm going to actually do E first. E to the 0.045, 25 power. And I'll take that times 8,218.16. Oops, I did 6 cents. Okay, and I get 25,000 still. but we're looking at $313.70. Okay, so we're looking at a difference about $313. That's over 25 years, okay? And that wasn't a huge amount of money, but if the money was quite large, that amount would get bigger, okay? The amount L of a certain radioactive substance remaining after T years decreases according to this formula. So here's another formula that involves E. That's not interest. B is the initial amount of radioactive substance. If 2,000 grams are left after 6,000 years, how many grams were present initially? Okay, so L is what's left. We're going to go with L being 2,000. So this is going to be 2,000 here. E to the, it says negative 0.001. Is that, make sure you count your zeros. T, okay, so negative 0.0001. How many times are we talking about? 6,000 years. That's ridiculous. Okay, 6,000 years. All right, so if I take, and I disagree with how they're doing this. They actually gave a decimal approximation for this. And I would rather just change this to E to the, hope I typed this in right, negative 0.6. Divide both sides by E to the negative 0.6, 2,000, divide by parenthesis, E to the negative 0.6. And I get 3,644.24. And that's it says approximately. The book cuts it off to 3,644. The book also gave me a decimal approximation for this E value, which I disagree with. I think you should keep the entire number as long as possible, okay? Initially, there were about, you can even round it if you wanted to, but I'm just going to leave it with 3,644 grams of the radioactive substance. Okay? With these irrational numbers, keep as much of the number for as long as you can in your calculator. Okay, this is your homework assignment. You can jot that down because that's what we're going to be working on in class when I see you next. Okay, see ya.